2,000 years ago, Roman builders poured a material that still stands against sea, storm, and time. Why does their concrete endure while so much of ours begins to fail within decades? Welcome to Echoes of Civilizations, where we explore the enduring foundations of the ancient world with care and historical integrity. In today's journey, we look closely at the science behind Rome's remarkable resilience. If you value thoughtful, research-based storytelling, consider subscribing and joining our growing community. Thank you for being here and spending this time with us. For more than 2,000 years, the concrete of ancient Rome has endured wind, rain, saltwater, and seismic tremors, yet many of its structures still stand with quiet dignity. The Pantheon, completed in the 2nd century of our era, continues to shelter visitors beneath the world's largest unreinforced concrete dome. Along the Mediterranean coast, Roman piers and breakwaters remain locked against the sea, resisting waves that have battered them since antiquity. On the Appian Way, the great Tomb of Caecilia Metella rises in solemn silence, its massive cylindrical form still intact despite centuries of weathering. These monuments were not preserved in ideal conditions. They survived in the open air, in marine environments, and across generations of political and social change. By contrast, many modern concrete structures begin to crack and deteriorate within decades. Bridges require constant repair. Seawalls fracture under chemical attack. Reinforced concrete, though powerful and versatile, often struggles against corrosion, alkali reactions, and internal stresses that slowly weaken its structure. In a world equipped with advanced chemistry, industrial precision, and computer modeling, it is unsettling to admit that a material formulated in antiquity can, in certain contexts, outlast our own. This contrast has inspired a serious scientific question rather than nostalgic admiration. What exactly gave Roman concrete its extraordinary resilience? Was it simply the presence of volcanic ash, long recognized as a key ingredient? Or did deeper chemical and structural processes unfold within the material over centuries, strengthening it instead of degrading it? In recent years, 2 major research efforts have brought new clarity to this mystery. A 2021 study of the Tomb of Caecilia Metella examined the mineral composition and long-term transformations within its concrete, revealing unusual chemical interactions that enhanced cohesion over time. Then, in 2023, another investigation identified distinctive lime clasts formed through a process known as hot mixing, uncovering a mechanism that allowed the material to heal its own cracks. Together, these findings shift the story from legend to laboratory evidence. They suggest that Roman engineers were not merely fortunate in their materials, but deliberate in their methods. The answer to Rome's enduring concrete lies not in myth, but in chemistry patiently unfolding across the centuries. To understand this endurance in concrete terms, we turn to a single monument that has watched the centuries pass without surrender. The Tomb of Caecilia Metella stands along the Via Appia Antica, the great Roman road that once carried armies, merchants, and statesmen out of the capital and into the wider world. Built around 30 BCE, at the turning point between Republic and Empire, the structure rises approximately 21 meters high and measures about 29 meters in diameter. Its massive cylindrical tower rests upon a square base, forming a silhouette that remains unmistakable against the Roman sky. More than 2 millennia after its construction, the tomb is still among the best preserved monuments on the Appian Way. Its outer surfaces bear the marks of time, yet the core of the structure remains solid and cohesive. This is not a fragile ruin barely clinging to existence. It is a monument that continues to project weight, stability, and intention. The durability of its concrete is not an isolated accident, but part of a broader tradition of Roman building that had already reached a high degree of refinement by the late Republic. Caecilia Metella herself belonged to an aristocratic family, and was connected by marriage to the powerful lineage of Marcus Crassus. The decision to erect such a monumental tomb on one of Rome's most important roads reflects both status and ambition. Yet prestige alone does not explain the engineering achievement. The tomb exemplifies construction techniques that had been systematized and described by the Roman architect Vitruvius, who was writing during the same transformative era. In his treatise on architecture, Vitruvius outlined methods for building thick walls composed of coarse brick or volcanic rock, aggregate bound together with mortar made from lime and volcanic tephra. He observed that such materials, when properly combined, would endure over a long passage of time without falling into ruin. The fabric of the tomb aligns with these descriptions. Its concrete consists of large volcanic aggregates embedded within a lime-based mortar enriched by volcanic ash. This was not improvised experimentation. It was the application of a well-understood material system, developed through experience and observation. By the late Republican period, Roman builders had already learned how to exploit the chemical reactivity of volcanic materials, especially those sourced from regions near the Bay of Naples, to produce durable structural cores. Seen in this light, the Tomb of Caecilia Metella is more than a funerary monument. It is a testament to a mature engineering culture. Its survival is not the product of luck or exceptional circumstance, but the outcome of deliberate choices in material selection and construction technique. In its silent mass, we encounter not only memory and lineage, but the disciplined knowledge of Roman builders who understood that true permanence begins deep within the walls. When researchers turned their attention to the interior fabric of the Tomb of Caecilia Metella, they were not searching for romance in stone, but for measurable evidence. The 2021 study, led by scientists at MIT and collaborating institutions, focused on the mineral composition and long-term transformations within the concrete itself. What they found was not a mysterious lost ingredient, but a subtle interplay of materials that had been quietly evolving for more than 2 millennia. The mortar binding the structure is composed of lime combined with volcanic tephra, porous fragments of glass and crystals produced by explosive eruptions. Embedded within this matrix are coarse volcanic aggregates that include leucite, a mineral notably rich in potassium. At the heart of the hardened mortar lies a binding phase known as calcium aluminum silicate hydrate, often abbreviated as CaSH. This phase forms the structural glue of the material, creating a cohesive network that locks aggregates together. To understand how this system changed over time, researchers employed high-resolution analytical tools such as scanning electron microscopy, X-ray diffraction, and Raman spectroscopy. These methods allowed them to observe the microstructure of the mortar and identify the crystalline phases present after 2,000 years of environmental exposure. Their findings revealed that the concrete had not remained chemically static. Instead, it had undergone a gradual transformation driven by the movement of water through the walls. Over centuries, rainwater and groundwater percolated through the thick masonry of the tomb. As this water interacted with the volcanic aggregates, leucite crystals slowly dissolved, releasing potassium into the surrounding mortar. In modern concrete, elevated levels of potassium can contribute to alkali-related reactions that form expansive gels, leading to microcracking and eventual deterioration. Such processes are well documented in contemporary infrastructure and are often a source of costly damage. Yet within the Tomb of Caecilia Metella, the presence of potassium appears to have had a different consequence. Rather than triggering destructive expansion, the released potassium contributed to a reorganization of the CaSH binding phase. Researchers observed domains within the mortar that exhibited a refined nanocrystalline character. These remodeled regions suggest that the binding matrix had been altered at the microscopic level, developing new configurations that enhanced cohesion. A revealing comparison can be made with the concrete used in the markets of Trajan, constructed more than a century later. In that structure, the mortar contains significant amounts of a mineral called stratelingite, in addition to CaSH. In the Tomb of Caecilia Metella, however, stretolingite is much less prevalent. The difference points to variations in the volcanic source materials and in the chemical pathways that unfolded over time. In the case of the tomb, the potassium-rich environment fostered a distinct evolution of the binding phase, reinforcing the interface between aggregates and mortar. These interfacial zones are critical to the durability of any concrete. They are the regions where coarse fragments meet the binding matrix, and they often represent the weakest link in modern materials. In the tomb, however, the long-term remodeling appears to have strengthened these zones, rather than weakened them. The microstructure did not simply endure the passage of centuries, it adapted within it. The scientific insight emerging from this study is both precise and profound. The durability of this ancient concrete cannot be explained solely by its initial composition. It is the result of chemical processes that continued to unfold long after construction was complete. Through the slow dissolution of leucite and the gradual reconfiguration of the CaSH network, the material developed a capacity to reinforce itself over time. In this way, the Tomb of Caecilia Metella stands not only as a relic of Roman ambition, but as evidence of a material system that matured with age, growing more cohesive as the centuries advanced. If the 2021 study revealed how Roman concrete evolved over centuries, the 2023 research uncovered something even more startling. It suggested that part of the material's resilience was embedded at the very moment of its creation. Hidden within many samples of ancient Roman concrete are small, bright white inclusions, often only millimeters in size. These fragments, known as lime clasts, had long been noticed by researchers. For years, they were commonly interpreted as signs of careless mixing or incomplete blending of raw materials. In a modern industrial context, such irregularities might indeed suggest poor quality control. Yet this assumption never fully satisfied investigators who were struck by the otherwise remarkable sophistication of Roman construction. In the 2023 study published in Science Advances, a team led by researchers at MIT revisited these lime clasts with fresh scrutiny. Using high-resolution imaging and chemical mapping, they examined their composition and internal structure. What emerged was a different story. These inclusions were not random defects. They were composed of calcium-based compounds that bore the signature of exposure to very high temperatures during the mixing process. This evidence pointed to a deliberate manufacturing strategy known as hot mixing. Instead of relying solely on slaked lime, which is produced by combining quicklime with water before incorporation into mortar, the Romans appear to have used quicklime directly in the mixture. Quicklime reacts exothermically when it comes into contact with water, generating significant heat. That elevated temperature within the fresh concrete would have enabled chemical reactions that do not occur under cooler conditions. The researchers concluded that this hot mixing process likely accelerated setting times and led to the formation of high-temperature associated compounds within the material. Within the lime clasts themselves, the hot mixing created a distinctive brittle and nanoparticulate architecture. These fragments became reservoirs of reactive calcium, embedded throughout the hardened concrete. Their structure made them particularly susceptible to fracture along emerging microcracks. Rather than acting as weak spots, they became strategic sites for future repair. The proposed mechanism of self-healing is both simple and elegant. When small cracks begin to form in the concrete over time, they tend to propagate through the high surface area lime clasts. As water enters these newly formed fissures, it interacts with the reactive calcium contained within the clasts. This reaction produces a calcium-rich solution that can migrate into the crack. As conditions stabilize, the dissolved calcium can recrystallize as calcium carbonate, effectively sealing the fracture. In some cases, it may also react further with surrounding pozzolanic materials, strengthening the composite structure even more. To test whether this mechanism truly accounted for the durability of Roman concrete, the research team produced experimental samples using both ancient-inspired formulations and control mixtures without quicklime. They deliberately introduced cracks into the specimens and allowed water to flow through them. In the hot mixed samples containing lime clasts, the cracks sealed within approximately 2 weeks and water flow ceased. In contrast, samples made without quicklime showed no such recovery. The cracks remained open, and water continued to pass through the material. These results support a striking conclusion. Roman concrete was not merely resistant to damage, it possessed an intrinsic capacity to respond to damage. The integration of quicklime through hot mixing created a distributed network of reactive inclusions that could activate when needed. In modern materials science, such behavior is described as self-healing. In the context of Roman engineering, it reflects a practical understanding that materials exposed to time and environment must be capable of adaptation. Seen in this light, the lime clasts are no longer imperfections. They are evidence of intentional design. Through the controlled use of heat and reactive lime, Roman builders produced a concrete that could close its own cracks and restore its integrity long after the builders themselves were gone. It is a reminder that durability does not depend solely on initial strength, but on the ability of a material to endure, respond, and renew itself across the centuries. To fully appreciate what sets Roman concrete apart, we must look closely at a region that engineers know to be decisive in any composite material: the interfacial zone, where coarse aggregates meet the surrounding mortar, often determines whether a structure will endure or fail. In modern concrete, this boundary can become a site of vulnerability. One well-documented process, the alkali-silica reaction, occurs when alkalis within the cement interact with reactive forms of silica in the aggregates. The result is the formation of an expansive gel that absorbs water and swells. Over time, this swelling generates internal stresses that lead to microcracking. These cracks frequently originate or widen along the interface between aggregate and paste, gradually weakening the entire system. Such deterioration illustrates a material fighting against its own chemistry. The very reactions that occur within modern concrete can undermine the bonds that hold it together. Once the interfacial zones are compromised, water and salts penetrate more easily, reinforcing a cycle of damage. Maintenance and repair become inevitable, and longevity depends on constant intervention. The evidence emerging from the studies of Roman concrete presents a different pattern. In the Tomb of Caecilia Metella, researchers observed that the interfaces between volcanic aggregates and the surrounding mortar did not simply remain intact by chance. Instead, they appear to have undergone a slow and continuous remodeling. As potassium released from dissolving lucite interacted with the calcium-aluminum silicate hydrate binding phase, the microstructure of the mortar evolved. Nanocrystalline domains formed, and the bonding regions between aggregate and matrix were reorganized. Rather than swelling and separating, these zones seem to have become more cohesive over time. The findings from the investigation of lime clasts reinforce this interpretation. When microcracks develop and intersect reactive lime inclusions, the resulting calcium-rich solutions can precipitate as calcium carbonate within the fissures. This process effectively restores continuity across damaged interfaces. The interfacial zones are not passive boundaries. They are active regions capable of responding to environmental change. Water, which often accelerates decay in modern systems, becomes a participant in strengthening the Roman material. Taken together, the two lines of research converge on a unified insight. The durability of Roman concrete cannot be attributed to a single ingredient or isolated reaction. It lies in the long-term behavior of the interfaces, where aggregates and binding phases meet. In these critical zones, chemical transformations did not produce destructive expansion. They fostered reorganization, densification, and repair. The material did not remain frozen in its original state. It matured within its environment. This capacity for evolution marks a profound contrast with many contemporary formulations, where modern concrete often experiences progressive weakening at its internal boundaries. Roman concrete demonstrates a capacity for sustained cohesion. The interfacial zones, instead of becoming sites of fracture, became sites of renewal. Over centuries, the fabric of the material did not unravel. It adjusted, rebalanced, and in certain respects strengthened. In that quiet, microscopic transformation, we glimpse the deeper reason why these ancient structures continue to stand with such steadfast calm. The renewed understanding of Roman concrete does not remain confined to archaeological curiosity. The researchers involved in these studies have made clear that their work is oriented toward the future as much as the past. By identifying the chemical mechanisms that contributed to long-term durability and self-healing, they are actively exploring improved cement formulations inspired by ancient practices. The aim is not to replicate Roman construction exactly, but to adapt its underlying principles within a modern scientific framework. One area of interest is the development of more durable concrete that incorporates controlled forms of hot mixing and reactive lime components. The experimental evidence showing that cracks in hot mixed samples can seal within approximately 2 weeks offers a tangible demonstration of how such strategies might extend the service life of structures. Rather than relying solely on external repairs, materials could be designed with built-in responses to microcracking. This line of research is moving toward practical applications, with efforts underway to commercialize modified cement systems based on these findings. The implications extend into emerging technologies as well. Researchers have suggested that more durable formulations could improve the performance of three-dimensional printed concrete. As construction methods evolve, especially in automated and additive manufacturing processes, the long-term stability of printed layers becomes critical. Integrating self-healing or enhanced interfacial behavior into such materials could significantly strengthen their reliability over time. Beyond structural performance, the environmental dimension is equally significant. Cement production currently accounts for roughly 8% of global greenhouse gas emissions. This figure reflects the immense scale at which concrete is manufactured worldwide. If structures require frequent replacement or extensive repair within a few decades, the cycle of production and reconstruction continues to drive emissions. By contrast, materials that last longer reduce the need for new cement, lowering the cumulative environmental impact over time. The researchers involved in these studies have emphasized that increasing the functional lifespan of concrete can contribute directly to sustainability. Longer-lasting materials mean fewer resources consumed, fewer reconstructions, and less energy expended in manufacturing, alongside other innovative approaches, including formulations designed to absorb carbon dioxide from the air. Improved durability represents one pathway toward reducing the climate footprint of the construction industry. In this context, the study of Roman concrete becomes more than an exploration of ancient ingenuity. It offers data-driven guidance for present challenges. By examining how lime clasts, hot mixing, and long-term mineral transformations contributed to resilience, scientists are identifying strategies that may lead to stronger, lighter, and more environmentally responsible building materials. The past does not replace modern engineering, but it informs it. In the enduring walls of Rome, researchers see not nostalgia, but a foundation for building more wisely in the centuries ahead. When we gather the evidence together, a clear picture begins to emerge. The extraordinary durability of Roman concrete does not rest on a single miraculous ingredient. It is not explained by volcanic ash alone, nor by lime in isolation. Instead, it arises from the interaction of multiple components and processes that unfolded across time. The pozzolanic chemistry created by combining lime with volcanic tephra, formed a resilient calcium-aluminum silicate hydrate binding phase at the heart of the material. Within that matrix, volcanic aggregates containing potassium-rich lucite gradually interacted with infiltrating rainwater and groundwater. Over centuries, the slow dissolution of lucite released potassium that contributed to the remodeling of the binding structure at the microscopic level. At the same time, the deliberate use of quicklime through hot mixing introduced lime clasts that acted as reactive reservoirs. When cracks formed, these inclusions enabled the precipitation of calcium carbonate, sealing fissures and restoring continuity. Across all of these mechanisms runs a common thread. The interfacial zones between aggregates and mortar did not simply endure passively. They evolved. Chemical transformations at these boundaries strengthened cohesion rather than undermining it. The material was not fixed in a static state after construction. It continued to change in ways that reinforced its internal structure. Based on the findings of the 2021 and 2023 studies, Roman concrete can be understood as a system designed, whether intentionally or through refined empirical knowledge, to gain resilience over time. Its strength was not confined to the day it hardened. Through pozzolanic reactions, lucite-driven remodeling, hot mixing with quicklime, and self-healing lime clasts, it developed a capacity for long-term reinforcement. In that slow and steady transformation lies the deeper explanation for why so many Roman structures still stand, bearing quiet witness to an engineering tradition that built not only for the present, but for the centuries that followed. As we step back from these ancient walls, we are reminded that history is not distant stone, but accumulated human intention shaped by time. The study of the past deepens our understanding of what endures and why. Thank you for spending this journey with echoes of civilizations. Your curiosity keeps these conversations alive. If you find value in careful, research-grounded explorations of our shared past, you are warmly invited to subscribe and return for future episodes.